right into the presentation, and we have people coming, so I can spend a few more minutes on housekeeping. The call today is hosted by the Microfluidics Innovation Hub. You see pictures of 4 people, which are co-presenters today. Janine Brommert from Temicon. Maybe you can quickly raise your hand, Janine, so that people recognize you. We have Anja Haase from Joanneum Research, and she is doing her talk together with Mirko Loza from MRT. Here's Mirko. We have Jan Kafka from Inmold with us today, and finally Alvaro Conde from Micronit. Before we actually start with the presentation, dear guests, I would like to ask you if everybody is okay that we start with the presentation, or if not, if you would be so nice to raise your hand or send us a quick chat comment. Otherwise, we would actually be very, very happy if we could record the session today, as we would put it online. So far, I don't see anything, which tells me that we are taking this as a yes. Thank you very much. Here you see the content of today's webinar. Actually, that's myself, General Manager of the Microfluidics Innovation Hub, giving a short introduction on what I will be referring to as the MIH in the next couple of slides. We have then Janine from Temicon, who's talking a little bit about mastering and tooling, Anja Haase from Joanneum Research, and Mirko about the first technology in roll-to-roll imprinting. Jan Kafka will follow up with his specialities. And finally, we'll have Micronit on the backend services, and thereafter we'll have a question and answering session. I would kindly ask you to keep back your questions until the very end. We'll do our best to keep to the 60 minutes maximum with the presentation. And with these words, we will actually kick it off. A few words so that you understand who's hosting this session and where we actually come from. It all originated from Horizon 2020 program. There is 20 members being part of what is called the Next Generation Microfluidics Consortium, which has the ultimate target to come up with technologies and services to design the biggest platform worldwide for upscaling, testing, developing microfluidic chips. That's the idea behind it. When we talk microfluidics, what are we actually talking about? We are talking about buzzwords like lab on chip, organ on a chip, which come in different form factors like microfluidic chips on foils, imprinted ones, which we're actually seeing today. We see cartridges, we see micro plates, and we are handling medical diagnostics, chemical analysis, these kind of processes. But essentially, when we refer to microfluidics, we always talk about very small dimensions, low volumes. That's actually the idea. To give you a hands-on idea or example how this actually works, we have here microfluidic chips. There's a drop of blood coming in, flowing along this channel driven by capillary forces. On the right-hand side, what you see, it hits various reagents. A chemical reaction is triggered. In these cases, it's a chemoluminescent reaction, and this chemoluminescent reaction is being measured by a readout device. And in this case, we are talking about antibody detection by using a microfluidic chip. Over here, you see the waste chambers, because all the blood or salvia or whatever liquid it is needs to go somewhere. That's the idea behind it, so that you get a first idea on what microfluidics are being used for. I was referring to myself always as the general manager of the Microfluidics Innovation Hub. What is that meant to be? As part of this program from the European Union, we had to set up, or the consortium had to set up, a single entry point. This single entry point sells and markets all the services of the 20 members of the consortium. So whenever you have a inquiry, if you have a special need, you address the single entry point. The single entry point forwards the request to the right partner. So we identify the right partner. We bring the partners together, we coordinate the partners, and eventually we manage the project, which means that the business fulfillment, so the actual project is being done by one or multiples of the partners of the Microfluidics Innovation Hub. That's the idea behind it. This is also the reason why we, as the MIH, acting as the single entry point, moderate and host the call today. So we are talking microfluidics, and I mentioned we are offering a unique, very broad platform, which is being represented here as a production chain. The Microfluidics Innovation Hub literally offers every service necessary to design microfluidic chips, which starts with the development, optimization, or transfer of any kind of assays. As a second step, these assays will be transferred to microfluidic chip platforms. So first of all, you have to design a microfluidic chip. You have to simulate it. You have to do mastering and patterning, finally replication. We're going to look quickly into all the technologies available for replication today and compare them. You need to do some cases surface functionalization. What that actually means will be shown to you in a couple of slides. Specifically, we can add electrodes and sensors on top of those chips to read out specific signals that's being generated by the reagent. And of course, we also do backend services, which, for example, is simulation of these microfluidic chips. The third big step in this very long production chain is you need the readout devices. As I said before, you're going to trigger a certain chemoluminescent reaction, but you need a specific device that reads out this reaction and quantifies it. We have capabilities to develop those devices, to optimize them, or we can sell ready-to-go devices. So we have an outstanding width combined with quite a large depth on services available. You will hear today representatives of three elements of this value chain, mastering Temicon, roll-to-roll, Inmold, and Joanneum Research, which will introduce to you two different roll-to-roll techniques, and backend services presented by Micronit. Last but one slide before we hand over to Temicon. So why did we actually go for roll-to-roll production? What's the background? What's the benefit of this? Eventually, the major benefit compared to the traditional microfluidic chip manufacturing technologies such as micromilling, soft hard embossing, and even injection molding is that we go for high volume and low cost. You'll see in a moment why. This is more or less really obvious when you see how it actually works. And the second one is it has been identified that a lot of the design requirements when it comes to dimensions are being handled and addressed in a much better way by chips that have these that have dimensions in the range of about several micrometers up to 400 or 500 micrometers in depth or height, than by doing injection molded or hot embossing using those technologies. We also have a quick overview which summarizes actually what I just said, comparing traditionally known technologies on the left-hand side, more coming from the lab side, prototyping side, relatively low volume side, going to higher volume with respect to quantities here when I talk about volume, and finally roll-to-roll, which is ultimately targeting multiple millions of chips because it's a super high throughput, but don't be afraid of that. People already accept designs and quantities that are in the range of about 100,000 units in case they cannot be handled by any of their other technologies. As we're talking about super high volume, what comes with it is, of course, very low cost. We have time to prototypes, which are a little bit longer or definitely longer than, of course, with PDMS, so your lab and prototyping capabilities. A very high selection of material properties, which will, in quite a lot of detail, be explained to you. And as I mentioned before, all of these technologies, production technologies, are available. So you can come to us and say, would like to start prototyping with micromilling, move on to injection molding, but definitely we have on the back of our mind to move on to roll-to-roll replication in very high volume. So a quick picture so that gives you a feeling why we talk about super high volume. You see the throughput speed of roll-to-roll extrusion coating. Again, that's Jan Kafka from Inmold. And Anja Haase will talk a little bit more about UV imprinting. Before we come to this, as I mentioned before, we go to the very first step, which is mastering. And with these words, I would like to hand over to Janine Brommert from Temicon.
Hello, here's Janine Brommert from Temicon. I am working here as a project manager in the R&D, and at the MIH, as Ronald said, we are responsible for the mastering and tooling. So here's something about our company. So Temicon is a worldwide leading in serious production of micro-nano structured components, films, and functional surfaces. We are founded in 2005 and located in Dortmund 2 times, and Freiburg and Shenzhen, China. At the moment, we have 70 employees, and most of our production processes are taking place in the clean rooms, like the lithography or the roll-to-roll or roll-to-plate processes. And our core applications of our customer projects are lighting, displays, solar, optics, and life science. This slide shows our normally process chains. So we normally start with design. So our customer give something to us, or we do it on our own. So in some cases, like the optical applications. And if we have the design, we if we have the design, we start with the lithography processes. We have 2 different techniques. So we can do laser interference lithography. That is a technique where we produce periodic grating structures. And for this, we can produce master structures about upwards to 250 nanometers, and on substrate size up to 1 square meters. And if we have any other structures like microfluidic structures, we can we use UV lithography and can produce structures upwards 2 microns on substrate sizes up to 20 by 24 inch. If we have the master, we can do a metal copy of it with the electroforming processes. So we can copy substrate sizes up to 20 by 25 inch, and can produce substrates with thickness of 50 microns to 3 millimeters. And now we have the tool. We can use it for other applications at Temicon, like injection molding, roll-to-roll, imprint process, and the roll-to-plate processes. And at the injection molding process, so we can use the tool directly and replicate it into PMA, PC, or COC. And if we want to go to the roll-to-roll machine, we weld the flat tool to a cylinder and imprint areas up to 1 meters with a speed up to 60 meters per minute. And we usually use film thicknesses with 20 microns to 250 microns, and mainly use PET foils. And the other cases, the last option we have is the wall-to-plate imprint process. And it's in this case, we do a further copy. So we do an inverted copy of our tool and do imprints on PMA, PC, or glass on substrate sizes to 1.1 to 1.6 meters. Yes, and now I will explain the lithography process more in detail. So the given design is transferred into a little lithography mask. The structure is optically imprinted via UV irradiation into a photoresist, like bottom left. After development of the resist, the non-cured areas can be removed and only the cured parts of the structure remain. So like bottom right. And then the created cavities can fill up with the nickel during the electroforming process. And then, yes. So we have the now the master, and the master is sputtered to become contacted and processed with an electroforming plant. So like bottom left. Then nickel grow on the top of the given structures. So we have the first nickel shim, call it the father. The master is usually destroyed using the separation from the father, but the father can be used directly or is the origin of many copies, which makes the process much more cheaper. So all in all, male members of the family, so the father, the son, and so on, have the inverted structure of the master, and females, the original one. So yes, and this is our typically family process. So we have the father do the passivation and makes the next electroforming process, so the mother. And so we can save our origin and can invert our structures. Yes, and can invert our structure. Now, and the last two tooling processes, if we want to come to a roll-to-roll tool, or we want to process at the roll-to-roll, it is necessary to transfer it into a cylindric form. Therefore, this shim is bent and welded at two connected edges. And to grant sufficient flexibility of the shim, the thickness is usually between 150 and 200 microns. By connecting several shims, a tool area of then 1 square meter can be realized, while the seam lines can be reduced down to 30 microns width and 10 microns height. Yes. And the last foil, you can see some typical structures we produce, like some pillars or some microfluidic structures. And some general data at the end. We can produce feature sizes between 250 nanometers to 200 microns. In some cases, it's possible to do a two-layer structuring process, and we can vary the angle of the we can vary the flank angle of the structures. So typically we have a flank angle of 85 degree plus minus 3 degree. And normally we works with aspect ratios up to 3. And yes, in some cases, what we also offer is different coatings for shims and sleeves. Yes, that's all from my side. So thank you for the attention, and I would hand over to Anja Haase from Joanneum.
Okay, thank you very much. Everybody, please, if you have any questions, please hold them back, make some notes, because we have 3 more presentations. We can always go back to these slides. You can note down the page number. We can skip to the page numbers. All of this is possible. Now we move on to Anja Haase from Joanneum Research and Mirko Lohse from MRT, and they're going to tell us what they actually use these shims for and how they engage them in their process. And we go from here. Anja, please.
Thank you. Please one slide back. So I will talk. Yes, I will talk about roll-to-roll UV imprinting, and UV imprinting is a replication technique. So now we are in the replication process, and this special technique uses a material which is structured, and that's why I represent 2 companies. So it's only me going to give the talk, but there are 2 partners involved. Microresist Technology, they provide the material, and Joanneum Research, we do the structuring. And now on the next slide, I just give 1 slide for each company, a short introduction. Microresist Technology is a German company based in Berlin since 30 years. They have around 50 employees, and they're really specialized in providing innovative resins, polymers, photopolymers, so the whole broad bandwidth, also optical materials. And they formulate new materials, they do synthesis, they research new any kind of material you are interested in, and they also offer lithographic services. On the other hand, Joanneum Research is a research company. We are located in Austria. Overall, we have about 500 employees, but in the we have 7 different research units, but in the microfluidic area, we are around 20 people working. We have a pilot line, a UV imprinting pilot line. We use it for various applications, bionic surfaces, decorative films, optics, and today I'm touching the topic of microfluidics. But for all these applications, we do material development, simulation, design, mastering on a small scale, and upscaling, but only for pilot production use. Okay, so what is this UV imprinting I'm talking about? Well, it's a very simple replication technique, and you can replicate micro and nanostructures simultaneously. What you need is a stamp, so we get it, for example, from Temicon, which contains the structure you want to replicate. And you need a substrate, you coat it with a UV curable imprint resist, place the stamp on the substrate, then you cure it with UV light, you remove the stamp, and you have transferred the structure. So very simple, and the beauty is you are independent of the optical wavelength. The letter resolution can go down to few nanometers, and you're also very flexible with respect to geometries, sizes, and forms. And this process we have transferred to it has been transferred to a roll-to-roll process. Same principle, so the picture on the left shows the coating of a liquid resin on a blue substrate, so beneath there's the blue substrate, and the stamp is rolled up, as has been shown by Temicon, and while the resin is in contact, it's cured with UV light and the structure is transferred. And the picture on the right probably is well known to all of you. You have a winter tire with a profile, and when you roll over freshly fallen snow, you can transfer your structure. So it's not roll to roll in this case, it's roll to plate. The street is the plate, but it's the same principle. The key features of this imprinting process is that you can replicate structures with aspect ratio higher than 2:1, with a web speed up to 30 meters per minute on any kind of substrate. In our case, normally it's polymer, can be PT, PEN, COC, PS, whatever you think of. It has to be transparent, and the thickness of the substrate can range between 20 to 250 micrometer. It has to be rollable afterwards, so it can't be too thick because then it's too stiff. Our key feature is the resin, which I'm going to touch in a second, and the structures you can replicate are 2-dimensional, 2.5D, several layers up to 150 micrometer or even thicker. And I'm just going to show a very short sketch of this imprinting process. To show on the next slide. Yeah. So it's very shortly only showing how it works. The blue is the resin. You can see the structure on the shim, on the sleeve, and then it's already structured when it passes the UV light. And on the next slide, you can see a picture of our pilot line with these different features we have. So on the left side, we have the resin application. In this case, we have 2 possibilities. We can use gravure printing for thin layers, and slot die coating for thicker layers, and thick means around 100-150 micrometer thick resin layers. The web width in our pilot line is about 30 centimeter, and the speed can vary between 0.5 to 30 meter per minute. For the microfluidics, we are talking about up to 5-6 meter per minute. And for quality control, we have installed an inline camera which can take simultaneous picture of each imprinted structure, and a wet thickness control for the beginning for the resin application. Okay, now I'm coming to the heart of the imprinting process, the material. As I mentioned, we are using a resin, a UV curable resin. And if we are talking about microfluidics, the relevant properties for resins is you want a fast curing because you want to go in roll to roll. You want low viscosity, otherwise it's difficult to apply the resin. And now especially focused on microfluidics, you want a low water contact angle. If you go for a capillary-driven chip, you don't want any swelling if you fill in liquids because the chip should remain the same size. You don't want cytotoxicity if you are talking about cells, and low autofluorescence for readout. And possibly you also would like to provide anchor groups for further biofunctionalization. Nowadays, everybody's talking about bio-based materials, and that's also something we take into account. So all in all, the parameters can be really adjusted to customers' needs. And on the next slide, you can see a nice material structure combination. So we have the same structure. You can see the structure graph at the bottom. So it's V lines on the left side standing out of the substrate. So it's really a V line standing out, and a very hydrophobic resin. And you can really see that the water droplet, it's a colored water droplet, it's really dancing on the substrate because it's so hydrophobic. Then we inverted the structure on the right side. Now we have V grooves and a water droplet in a very hydrophilic resin. And now we have a really open capillary-driven flow. The water droplet is only driven in the open V channels. So really, if you have the right properties on combination of material and structure, you can really adjust the surface properties. Now I'm giving 3 examples where we used roll-to-roll UV imprinting for different applications. The first example is a neuronal cell assay, which is used for drug testing, drug screening. And the problem if you're using neurons for drug screening is that the neurons tend to grow really randomly and on top of each other, and they are interdigitated, and then they have outgrowth. It's really hard to distinguish which outgrowth belongs to which neuron, but that's essential if you want to screen a drug. So our approach was to imprint a microfluidic mesh with a channel width of 5 micrometer. And at the crossing points of these channels, the larger neurons are situated because they cannot enter the small channels. And then they're really fixed to this place, and then they can communicate via these small channels. So this imprint pattern was fabricated with a speed of 1 meter per minute into an MRT resin. And then the substrate foil was mounted to a microtiter plate, as you can see pictures on the left side. And with this, we could show excellent cell compatibility. So the neurons grew and also other cells grew nicely in this pattern. We had a very low background signal due to the optimized autofluorescence of the resin and the substrate, of course, as well. And the readout was much easier in the first preliminary assay tests due to these well-separated neurons. The second example I want to show is a so-called origami chip. And the beauty of this is that you can fold these plastic foils in several layers on top of each other. So you maintain the same substrate size, you have the same outer dimensions, but you can integrate more functionalities. So what you do is you structure your microfluidics channels on one side of the substrate. Then you use a laser for engraving the folding lines. You fold them together. They are laminated by technique Micronit is presenting in the presentation 2 afterwards. But then you have a folded chip. And then you really have the same outer dimensions, but several functionalities. We did this with a resin developed at Joanneum Research with an imprinting speed of 1 meter per minute. And in our example, which is not shown here, but we could also integrate amplification methods like LAMP. On the next slide, there's just a short video of a colored liquid entering several layers of this folded chip. Now it's in the first layer. Now it's already in the second layer, so it has passed the first chip layer, and now at the end, it comes to a third layer. You can see the dark blue color coming from the right side because it's 2 layers above the other one. So I shortened the video a bit to make it faster in this presentation. Okay, and my last example is the roll-to-roll based production of a lab-on-foil chip. So the basis for this development was an already existing and commercially available injection molded chip for detecting different types of analytes. In our case, we used this detection of antibody tests of corona. So we had this injection molded chip, and the idea was to transfer this design to a roll-to-roll imprintable one. There's also a commercial readout system based on chemoluminescence, and we could show this transfer of the fluidic structure to roll-to-roll imprinting. You can see the video where it's imprinted with, I think in this case it's 1 meter per minute, but we can normally we drive this with 4 meter per minute in a resin by MRT, micro-resist technology. The chip height, I think the fluidic channels are around 120 micrometer deep. And when we closed those chips with a bonding technique, we could show excellent filling of those bonded chips due to intrinsic hydrophilicity of the resin. And the adjusted surface chemistry allows for direct spotting of the antigenes. And with this replication technique, maybe that's what I haven't mentioned yet, is that we can really go to high throughput, fabricating up to 1,000 chips or more per hour. So the next slide just has some more pictures of this example. So you can see the commercial readout system in the middle and the injection molded chip at the left side and the roll-to-roll imprinted in the middle. And when you look at the graph, you see that we have comparable signal heights with both chips. So it's really compatible and we can transfer this production to roll-to-roll imprinting. Okay, this brings me to my conclusion on the next slide. So roll-to-roll UV imprinting is, to my opinion, really a very nice and versatile technique. We can replicate multiple different structures, so not only microfluidics, but also optics, as I mentioned in the beginning. We have integrated inline control to really ensure also quality control. We can go to high throughput. And I think the really distinction to our next technique is that we can adjust the properties by the combination of materials and structures. Thank you very much for your attention.
Thank you, Anja. Good, as Anja just mentioned, we go on from one roll-to-roll, let's say, technique on to the next one. So roll-to-roll UV onto roll-to-roll extrusion coating with Jan Kafka from Inmold. Jan, please feel free to move on. I'm switching to the next slide. And you muted?
Yes, I am. Thank you. Okay, thanks for the introduction, Ronald. Yes, as mentioned, I'm representing Inmold, which is offering another roll-to-roll technology to the MIH. Our technology is based on roll-to-roll extrusion coating, which will be the focus of my talk today. Inmold is located in Denmark, more specifically on Zealand. That's a small island right beside the mainland. We are 20 kilometers north of Copenhagen. We have access to state-of-the-art state-of-the-art clean room facilities. Yes, thank you. And also access to large-scale extrusion coating facilities through a partnership with a packaging producer in Denmark. Now the next slide, please. The main difference what we have in roll-to-roll extrusion coating in comparison to the previously described UV anneal is that we use thermoplastic materials, thermoplastic polymers, in opposite to UV resins. And hereby the thermoplastic granulates are actually getting heated up, that you can see in the top part of the image onto the left as granulates, and they're extruded as a melt curtain into the nib of 2 rollers below. If there are structures on the large rollers, these structures are getting instantly replicated when passing the nib of both rollers, and then the film is cooled down and actually released on the other side. On the movie, you see how it looks like when the film leaves the structure to cooling roller, as in this case a film structured with microfluidic devices. And the next, yes. Inmold is offering different types of structured films, decorative, plasmonic, as well as hydrophobic films. And now recently also life science, films for life science applications, which I will describe in the following slides a little bit in detail. Why is roll-to-roll extrusion coating actually so interesting for life science? So first of all, as I mentioned, we use thermoplastic polymer that could be polypropylene, polystyrene, cyclic olefin copolymer. We can also investigate other polymers on request, which also means that you can actually, when coming from a part which is produced with extrusion coating, for example, with injection molding, for example, established chemical surface functionalizations can be directly transferred to the films. The same counts also for bonding methods like solvent bonding, ultrasonic bonding. These technologies can be directly transferred onto the film. Makes it actually very easy to scale up your process from injection molding towards roll-to-roll technologies. As we have production speeds of a couple of meters per minute, we actually can fulfill the increasing demands also of the microfluidic market, which is increasing right now. We upgraded our facilities recently to be able to produce films up to 500 micrometers. And that allows that the film actually are quite rigid. So we have a very high stability of the films. And as we produce films with a structured or with a large structured surface, if you look, if you compare the injection molded pieces with extrusion coated foil, then you actually reduce the bulk of the material, which means that you use less material for your final product. On top of it, if we have a thin film, we actually reduce also the distance between the sample and the detector. Makes it actually much more easier to detect reactions going on in your microfluidic device. We are actually limited when talking about the replication. We are only limited or mainly limited by the width of the roller. That means actually you can scale up your pattern surface, your microfluidic devices quite a lot, allowing the definition of super large microfluidic devices if necessary. As you can see in the picture on the right side, the second from the top with the circles, for aspect ratios up to 1, we have a relatively high degree of freedom to define microfluidic channels in various directions. And on the pillar structures, on the very lower picture, you can see that there is, for our technology, actually no draft angle necessary when talking about the replication of even high aspect ratio structures. The film thickness of 500 micrometers allows us also to produce multi-level microfluidic devices. Meaning we have, for example, a microfluidic device with energy directors on the left and right side of the microfluidic channel, allowing certain bonding. Yes, thank you. We can build up multi-level fluidic networks, like shown on the very left picture, where we have a large, deep microfluidic channel with smaller channels in perpendicular direction. We can also replicate stop valves, as shown in the second picture from the left. And up to the point that we can even not only 2, also 3-dimensional microfluidic devices, as also shown in the right picture, lower picture, where we have one channel entering from the top, having a step to a 200 micrometer deep channel and having the energy directors left and right of the microfluidic device. So having basically 3 different levels combined in one system. Here are 2 examples which we realized where we realized the replication within the mentioned project, next-gen microfluidic. We were responsible for the replication, so chip design and mastering, as well as testing were done by other partners of the project. To the left, we see a neuron chip that is similar to the chip Anja already showed in the previous part of the presentation. It's made to grow neurons on the left and the right side, and cavities left and right side, which are separated through a bridge. The bridge has very, very long, small channels where neurons send their axon through the small gaps and form a common network. Start communicating, and that can be then used, for example, for drug screening. What you see in the SEM images is the bridge having a bulk part, and on top of that bulky wall, we have very, very small, long channels connecting both sides of the chip. The presented channels have an aspect ratio of 2, so that means they are 5 micrometers in width and 10 micrometers in depth. On the right side, we see a sensor for bioreactor control. Hereby, it is we have an inlet. Yes, the liquid is inserted into the chip. All cavities are filled properly. And then we have in the end a capillary pump, which actually extracts all the fluid from the microfluidic channel in the front. That is in that way important that we actually have an isolated detection chamber, which is needed for an enzymatic reaction or detection, basically. So what we can see is having the detection centered, completely isolated from the fluid in the end. Yes, so to ensure our high replication, we installed an inline quality control. To the left, you see an installed optical microscope. On the right side, a confocal microscope. The optical microscope is capable of detecting or to analyze the imprinted structures optically. The confocal microscope is to ensure the proper imprint depth of the structure. Yes, so to summarize my part, I presented a large-scale replication technique based on thermoplastic polymers. The advantage here is that the surface functionalization and bonding techniques used for example, injection molded parts can be directly transferred to foil we produce. We have a unique replication system. We can make complex fluidic systems with on films up to 500 micrometers, and we have installed an inline control to actually to ensure high quality and also to adjust parameters during the production. That was my part in respect to the patterning. I would now hand over to Alvaro, who's presenting the back-end process like bonding and cutting.
Thank you very much. So Alvaro takes over those chips, and now let's hear what Alvaro and Micronit is actually doing with them in the next production steps. Alvaro, please go ahead.
Production. So Alvaro Conde here, Senior R&D Scientist at Micronit. I'm going to talk a bit about the backend processing of these foils. So if you can go to the next slide, Ronald. Yes, so before we do that, I'll explain a bit about Micronit. So we've been founded in 99, so it's a bit more than 20 years. We're a spin-off of the University of Twente. We're based in Enschede in the Netherlands, it's the far east. We're very close to Germany, actually, and we also have another part of the company in Dortmund in Germany. We work with more than 1,000 customers across more than 50 countries, and we work also with top universities and companies around the world. We're more than 120 people. The exact number, I'm not really sure, but it's somewhere around that. And we are also quite diverse in terms of nationalities. And something to mention is that with ISO 9001 and ISO 13485 certified. And what you see on the right, yeah, it was just a picture of the of our new build that is coming up next year. That is aimed to be CO2 neutral. This is a bit of what we do at Micronit. So we work with microfluidics and other technologies to create, for example, automated workflow systems, systems for high content, also for high throughput synthesis or analysis, devices for digital microfluidics, integration also of integrated circuit technology and sample to answer systems. And the idea is to combine microfluidics and MEMS to create systems with a higher value. Next slide, please. All right, so coming back to the foils, I'm going to explain the backend processes and why they're needed. So as you've seen in some of the pictures along the previous slides, these foils normally come out structured, but they don't have holes, for example. So we need to create those after patterning. And normally there is also processes in between. For example, for some products, we might need to do spotting. I just included here. I'm not going to go very deep into that, but it might be needed. And then after that, we need to close the channels, we need to bond them and to separate them from the main web to create the single devices. Next slide, please. Yeah, so this is just to give you a visual image of how the foils look like. And on the right hand side, you can see what we call a chip. And you can see there that it does not have holes and is still on the main web. So this is what we aim to do when we do hole drilling and singulation. All right, for hole drilling, if we look at the left hand side, we start with the pattern foils. In this case, the pattern is one of the products that you've seen across the presentations. And they normally integrate fiducials that we can use to align with, for example, a laser processing system. And with this laser system, we can create the holes for example, an inlet or vents in this case. And on the top, you can you can see some examples of those. You can see that this will drill with the ultra short pulse laser, and you can see the very good quality of the cuts. Next slide, please. Yes, for spotting, this is just very simple. This is not really what we call the backend processing, but it's in between. So that's why I included it here. And the idea is that we use a spotter. In this case, Joanneum Research has available a roll-to-roll spotter that can actually do this. And we can put different biology, for example, antibodies or proteins or things that we like to use for the different products. We can also integrate a surface activation step, for example, plasma or corona treatment to enhance the addition of these components. Next slide, please. All right, and then finally we have bonding. The idea here is to put a lid on top of those foils that have already the holes and the spotted reagents. And to do this, we have different bonding techniques depending on the production method. For extrusion coating, which is the method that Jan mentioned, that uses thermoplastic, we have 3 techniques that were validated, and also we also have a 4th one, which is laser welding, that's still under investigation. And for the UV nil foils, there is a method that uses partially cured resin that I will also explain on the coming slides. All right, so this is an overview of the roll-to-roll thermal lamination and solvent-assisted bonding for extrusion-coated foils. It's a relatively simple method, especially thermal lamination. It's just basically passing the structure foils along with a blank foil through heated rollers and applying also pressure between those nips. And then we can bond the foils continuously. Solvent bonding is very similar to this, but we apply a very thin solvent layer on the blank foil. And the advantage of this method is that it produces, it requires far less temperature to create a proper bonding. And this way we can preserve some of the biology that is integrated there. If we only use thermal lamination, we might actually damage what we already spotted. But we also need to be careful that these solvents don't actually affect the biology that we have there. So we need to ensure that it's completely evaporated either before or after bonding. Next slide. Here's some examples of the two processes. On the left-hand side, there is an example of the thermal lamination. In this case, a product aimed at SARS-CoV-2 detection using antibodies. And on the right-hand side, we have a solvent-assisted bonded device that was aimed at the neural cell culture. And there you can see on the red squared image the microchannels that were bonded by this method. And just as an example, those channels, I think Jan also mentioned, they are very small. They are 5 micrometers in width by 10 micrometers in height. There's also another technique available, which is called ultrasonic welding. Perhaps some of you are familiar with this technique. And the idea here is that we take advantage of structures that we can integrate on these foils called energy directors. If you look at the image on the left, you can see an overview of how this looks like. So we have our bottom piece that contains the microfluidic structures. We have energy directors represented by those triangular shapes. In this case, we cannot really do that with foils. I mean, it is possible, but it's more tricky. So we do them in a rectangular profile, but it still works. And then we apply ultrasonic energy using the transducer that you see there. And by doing this, we can obtain closed channels in a reliable manner. And the advantage of this method is that the heat is only concentrated where the energy directors are. What this means is that we can preserve the biology, and it's also a very fast method. It typically takes a couple of seconds per set of devices, let's say, and you can fit typically 150 by 150 square millimeters of devices. And the pictures on the right, they're just showing some images of the energy directors on the foils. You can see there a top angle view and cross-sectional view highlighting the energy directors. All right, so the image on the left is showing an overview of the setup. I'm not sure if the video will work, but it's just simply what you see on the top is the sonotrol, so the ultrasonic transducer, and at the bottom we have the foils, the structured foils, and also the lid, which is kind of the blank foil. And then that big tool over there goes down, applies pressure and also ultrasonic energy for typically less than a second, and then it goes up again, and we can start with the next set of chips. So it's what is called a step and go process. And the pictures on the right, they show some images of these foils that have been ultrasonically welded using this technique. And also some microscope images highlighting where the energy directors melted, creating the weld seam, and also a cross-sectional view of this, showing that it preserves quite good the cross-sectional profile of the channel. All right, so for the UV nil foils, as I mentioned, so we cannot really use thermal processes here because they're it's a different type of chemistry that is being used. But we do have available a technique in Joanneum Research that's been also patented that uses a foil that contains a very thin layer of uncured resin, the same resin that was used to produce the structures. But it comes with also a trick that the structures, they are not fully cured. So they're partially cured in order to maintain stability, but not fully cured that will prevent bonding. So, and this method is actually a continuous method. There is a video on the right that is actually showing this method in real time, how it's happening. And by doing this, we can actually achieve very good bonding quality in a continuous manner using also relatively low temperatures. Next slide. All right, so after we bonded these chips, if you can see on the left-hand picture, we have the chips that are bonded. They contain the biology that we need. They contain the holes, but we still need to separate them from the main web. And to do this, we rely again on laser processing because it's a very flexible process, and we can align with the fiducials that are imprinted there. And we end up with the devices that are separated as single chips. You can see a picture there also on the right-hand side of how these chips look like. And finally, we end up with what's called the lab on a foil, as you can see here. And Ronald just played a video of how this looks like. There were similar videos shown across the presentations, but this is just to highlight the end of the process, let's say. So we finalize with this device, and then it comes, of course, labeling and packaging, but this is not a part of this presentation. And I think that concludes with my slides. Ronald, yes.
Okay. Thank you, Alvaro. A super quick summary, actually 2 slides. One slide as a quick, let's say, visual refresher, because we have had 60 slides now over 60 minutes. For those of you who have questions. So we started with Temicon on the mastering side. They explained to us how they actually do the masters, which finally turned into shims. Those shims go onto the rolls, which are being used to imprint the patterns either on resins or on thermoplastics for Inmold. The first one's for Joanneum Research. Then we also included a discussion on microresist technology, which uses the resins for Joanneum Research, which uses this to be imprinted into. We then moved from Inmold, Joanneum Research, and microresists, who are responsible for the patterning, onto an intermediate step that might be necessary as we talk about reagents, which is spotting various reagents onto the chip before we move on to the backend services, which Alvaro just explained to you. And the backend services including cutting edges into the chip so that the air can get out. That's why the vent holes are in and the liquid gets in, which is called the inlet, which then finally the chip needs to be covered so that the liquid that's inside cannot spill out. This is when it comes then to what Alvaro explained, various possibilities for bonding. Before, as we have those chips on relatively large areas, we singulate the chips. And this is the singulation process, which as a very last step has been explained to us by Alvaro. So what you see here are 1, 2, 3 plus steps in this whole production chain. Last slide from the MIH, in case you're interested before we start with the questions. All of the services we explained plus additional services are being offered by the consortium via the MIH as the single entry point. And here comes a little bit on top of this. So a real nice candy is that you have access as customers to those services, and those services are being funded by the European Union. So we can provide budget up to 200,000 euros in case you are in need of multiple of those services for your innovation projects. We have the open call, as we call it, up and running until September 2023. You see more information on our website. You just have to apply for the funding, introduce our project to you, and you will be assigned partners from the MIH who will take care of this project. And what is normally also very interesting for customers, funding rate is up to 92% for SMEs and startups, and 50% straight for large enterprises. We take everybody from the European Union plus associated countries. The only exception is we cannot accept university and research and technology organizations. With these words, we can close the official presentation from the 5 presenters. Thank you very much for helping us out and giving those very nice insights into the technologies. I think it would be nice if you could turn on your cameras now, because we would start the question and answering session. So, dear audience, please feel free to raise your hand and ask your questions with respect to the last 60 minutes and 60 slides you've heard. I hope you made a reference with the slide number. Otherwise, please raise the question or directly address one of the presenters.